All right, hello, welcome back. Let's talk about this differential equation. We don't know how to deal with this yet, right? This is not homogeneous. If this was y double prime minus 3y prime plus 2y equals 0, we would know exactly what to do. We would be happy. We would kind of go, we would set up the polynomial, factor it, get ourselves probably y equals what? C1 e to the t plus C2 e to the 2t. Okay, they're very easy to solve, but I've got this e to the 3t here. It's like, what am I gonna do? Okay, so I got good news for you. It's really not that bad. What we're going to do is we're going to need to figure out something that fits this, and then we need to think back actually to what we did that other time where I had, y equals C1 e to the t and C2 e to the 2t. But you're going to need a little help along the way. So what I'm going to do is I'm going to say, well, your first guess should probably be y equals e to the 3t. See, does it work, right? So, guess y equals e to the 3t. Well, then y prime is 3e to the 3t, and y double prime is 9e to the 3t. And you can see when I plug in y double prime minus 3y prime, I'll have 9e to the 3t's minus 9e to the 3t's is 0, plus 2y would be 2e to the 3t. And 2e to the 3t is not equal to e to the 3t. This is troublesome. Okay? So this is not going to be a good guess, but we're kind of close. I feel like, especially since we're just multiplying by numbers here, if we had multiplied by different numbers along the way, I could probably get this to work, right? And while this 1, -3, and 2 is set, I don't necessarily have have to take 1e to the 3t. So what I'm going to do is I'm going to say, okay, I feel like I'm close. So I'm going to make a new guess. I'm going to guess y equals ae to the 3t, just for some a. That would mean that y prime was equal to 3a e to the 3t, and y double prime was equal to 9a e to the 3t. Then, this is I'm not gonna be able to just say this and, kind of mentally do the algebra. I'm gonna have to go in and I'm gonna have to take y double prime, 9a e to the 3t, minus 3y prime will be minus 9a e to the 3t. Oh, so I'm back to this 0 situation. I feel like kind of troublesome, but then I see I'll have plus 2a e to the 3t equals 1e to the 3t. Okay, this is good, right? Because this is 0. That's 2a e to the 3t equals 1 e to the 3t. This whole equation boils down to 2a equals 1 and a equals a half. So I've got a solution, right? I've got y equals, or was it 1/2 e to the 3t? If you want to, you can pause the video right now and take 2 derivatives of this and make sure it runs through correctly. It does. And so I really want to talk to you about the relationship between this one and the solutions to the homogeneous equation, like if this was 0. Okay? So I'm going to erase this off here, and then I'm going to kind of go in a different direction. Okay? So really, I probably should have started talking about this in the video titled Solutions to Second Order ODEs. Hey, really wish I had. Maybe by the time you're watching this, I will have re-recorded that video, and I will have already talked about this. We'll see. But I want to talk about the left side of this equation. Okay? And I think, I'm going to grab a color here. I'm going to kind of go over here. And I want to call this left side, consider it as an operator. And you don't really know about linear operators, but basically I'll tell you what you need to know about them along the way. Let's define L as a thing that takes in a function, y of t, and does this to it. Okay? It takes the second derivative, then it subtracts 3 copies of the first derivative, and then adds 2 of itself. Okay? Whatever that means. L of y, in this case, I'm going to let that equal y double prime minus 3y prime plus 2. 2y. Okay. Now for now, I'm just going to call it L of y because it's the left side of the equation. Like what happens to a function when I throw it through the left side of the equation? Well, if I just talk about, now I'm going to need to, talk about y. Maybe I'll call it y hat because this is like an important one. Okay. Well, it will be the case that L of y hat is equal to e to the 3t. Okay. And well, what you can go in and show, which is again the thing I didn't really show in the solutions to second order ODEs video, is that for, two functions, say y1 and y2, L of y1 plus y2 is going to be L of y1 plus L of y2. And the reason why that's true is the linearity of the derivative. And we know this from all the way back to the beginning of AP Calculus, that the derivative of a sum is the sum of the derivatives. That's why, we can do this without a second thought, right? If we have, f of x equals cosine x plus x squared, we know how to take the derivative of it. It's negative sine x plus 2x, right? The derivative of the sum is the sum of the derivatives. And that's why when I go, and I'm going to ask you to consider, what would happen to L of, well, what if y was equal to one of the solutions to the homogeneous equation, right? Like L of y equals e to the t. Okay, well, e to the t double prime is e to the t, minus 3 is negative 2 e to the t is plus 2. Okay, it's going to come back 0. So L of e to the t is equal to 0. Moreover, L of e to the 2t is also equal to 0. And, this is because y equals e to the t and y equals e to the 2t are solutions to the homogeneous equation, right? So the homogeneous equation y double prime minus 3y prime plus 2y equals 0. Okay. And because the sum of the derivatives is the derivative of the sum, and vice versa, basically because L is a linear operator, I can say that, well, L of y hat plus maybe even c1 e to the t plus c2 e to the 2t is going to be the sum of the results, right? It's going to be e to the 3t plus, oh, and then the constant multiple thing. Also, I didn't really mention that it's going to work out to be that, L of c1 e to the t is also going to be 0 for, reasons that you've seen already. And so, being a linear operator, it's going to respect constant multiples. L of ay is going to be a times L of y. Okay. But, so really I'll have, if I have c1 e to the t, I'll have c1 times 0, which is going to be a 0, plus, okay, L of e to the 2t is 0, so L of c2 e to the 2t is going to be c2 times 0, which is also going to be 0. Okay. Which is e to the 3t, which means that this right here, this is a solution to the original non-homogeneous differential equation. Which means that the non-homogeneous case, there's going to be hidden solutions, right? There's going to be hidden homogeneous solutions. And we just need to remember those. Okay? And the technique that I took to determine that it was 1/2 e to the 3t, like I said, okay, I assume it's going to be some kind of e to the 3t, and I'm going to figure out what kind of coefficient goes against it to make it actually work as e to the 3t. That's going to be called the method of undetermined coefficients. Okay? But I'm going to take a step back and talk about what did we do in general to show you how I would, attack this. All right, so what did we do there? What we really did was we took a linear second order differential equation, like we've been talking about all along. We let g of t not be 0, okay, for this whole time we've been talking about second order ODEs, we've wanted G of t equals 0. We've wanted P of t and Q of t to be numbers. Now we still want P of t and Q of t to be numbers. And I don't know that, in this, short course in techniques and differential equations that we'll actually go far enough to take P of t and Q of t to be not constants. But I'll tell you, it gets pretty nasty pretty quick. And what we wanted to do was we wanted to kind of just consider what happens when I take a function y of t and I take its second derivative, I take its first derivative and multiply it by q of t, and I take it and I take the first derivative by p, take the original by q. What happens there? And so what I said was, let L of y be kind of an operator that takes in a function and does something to it, right? Really, it's going to give you back a function, but let L of t be the thing that L of y be the thing that takes y's second derivative, then adds in takes its first derivative and multiplies it by p. Okay, and I'm just gonna, I'll write p of t. Got enough room. And then takes q of t and multiplies it by y. Now this is for a kind of given choice of p and q. Okay? Those are already set, right? So L of y is something that we're going to do to this function after we already know our differential equation. Right? It's not going to be a function, or it's not going to be an operator that takes in a function y and a function p of t and q of t. I'm not really trying to consider all of those cases. I'm just saying for a given p and q, that's what I'm going to let L of y be. Okay, and then I want to talk about, well, I know that there are solutions to let yh1 and yh2 be kind of the two kind of fundamental, or not even fundamental, just two solutions to the homogeneous differential equation. Say two linear independent solutions to the homogeneous differential equation. And so maybe rather than saying y double prime plus py prime plus qt equals 0, right? That's what I want these two to solve. They solve the homogeneous equation. But maybe I'll just call that L of y equals 0. Okay, that's going to be the homogeneous equation. And maybe I will underline that in blue, just in case I need to come back to that. And maybe I'll even write that down. All right, the homogeneous equation. Suppose I've got two linear independent solutions to the homogeneous equation. And then suppose that I found, like I did, I found that y equals, I called it y hat, so maybe I'll call it y hat again. It was 1/2 e to the 3t. Okay. So I'll say let y hat be a solution to the non-homogeneous equation, which I will underline in red. Well, that's not good. All right. Like I said before, L is a linear operator, so, and maybe I'll just write these things down. And I'm not going to go in and prove them. You could show it yourself using the linearity of the derivative, right? That if you have y1 and y2, then 2y1 plus 3y2 prime, what this is 2 times y1 prime plus 3 times y2 prime. This is what I'm talking about, the linearity of the derivative. Okay, and this is like what all of this is resting on, but I don't really want to get bogged down too deep in it because I want to show you how to solve the non-homogeneous linear second order ODE, right, with constant coefficients. So, it is the case that L of A plus B equals L of A plus L of B, and that the L of, some constant times A is C times L of A for some function A and B. These are true. Now, what I'm proposing is that because of these things, if I take y hat and I add it to YH1, homogeneous solution 1, and homogeneous solution 2, like I did in that example, I'll still get a solution to the red equation, to the non-homogeneous equation, L of y equals g of t. Okay? Right? And maybe I'll just show you what I'm talking about. So I'm saying that L of y hat plus C1 times homogeneous solution number 1 plus C2 times homogeneous solution number 2. Well, what I'm going to get is that's going to be, maybe I'll just carry this on through, L of y hat plus C1 times L of homogeneous solution 1. I know what happens when I run homogeneous solution 1 through that equation. So basically doing L to it, I'm going to get 0. And plus C2 times L of homogeneous solution 2. Okay. And that is going to be equal to L of y hat is g of t. And then, hold on, what's happening? Oh, yes, plus C1 times L of y of h1 is going to equal 0. Plus C2 times 0, same. Okay, which means that that's equal to g of t. So that means that this thing here solves the red equation. Okay? That's what I'm saying. Now you might be saying, wait a second, dude, shouldn't there be like a second one of these? Right? It's a second order ODE. We're used to having two linear independent solutions. Like there should be another kind of y hat, like a particular solution. And it turns out that there is not, and I will show you why. So I think I need to kind of clear all of this out. And I don't think that was necessary at all, actually, now that I think about it, so I'm just going to work over here. I'm going to say, suppose there was a second solution to the non-homogeneous equation that was linear independent from the first. That wasn't just some kind of constant multiple of the first. Okay. So suppose y hat 2 solves the red equation. If that's the case, maybe I'll again underline that in red to emphasize I'm talking about the non-homogeneous situation. Suppose y2 solves that, y2 hat, or y hat 2, whatever you want to call it. If that's the case, then L of y2 hat equals, I'm not sure what that was, L of y2 hat was equal to GT, but also L of y hat, or maybe I'll call it y hat 1, is also equal to g of t. So if I considered y hat 1 minus y2 hat and ran it through the left side of the equation, or did L to it, or whatever you want to call it, y hat 1 minus y2 hat, well, that's going to equal g of t minus g of t, or g of t minus g of t that way probably. Which means now that y hat 1 minus y2 hat is a solution to the homogeneous equation. Okay, so I've got myself a homogeneous solution right there. But I also know from before that all of the solutions to the homogeneous equation are going to be some kind of linear combination of the two linear independent solutions, which means that y1 hat minus y2 hat equals, some kind of combination of what yh1 and yh2, homogeneous 1 and homogeneous 2. So k1 yh1 plus k2 yh2 for some k1 and k2. All right? Which means that if I have one particular solution that solves the non-homogeneous, and I know the solutions to the corresponding homogeneous differential equation, I've got the general solution. That's what I've been building up towards. So the general solution is going to be y of t equals, well, it's going to be y hat plus some number of the first homogeneous plus some other number of the second homogeneous. And this should kind of be a little reassuring in the sense that you would think, second order ODE, before we knew that we needed two initial conditions to find a particular solution. And you wouldn't expect that you would need to find a third constant, right? That's also what I showed over here is that, right, since I've got one of these, just having a particular solution will then dictate the value of the constants here, okay? So I think it might be good for me to go back and work another example at this point. All right, so let's look at this one. This one, you might be saying, dude, this is the exact same example, and it's very close, okay? The point I want to point out is that e to the t is, the non-homogeneous part, but it's also one of the solutions to the corresponding homogeneous equation. And that's something we're going to need to be able to deal with. Okay? And so, if I'd gone through the same technique and been like, okay, I'm going to use undetermined coefficient, I'm going to say, I'm going to guess y equals a e to the t. Okay? Then y prime and y double prime are also going to be a e to the t. And when I plug this in, so I'll say, okay. Then when I go and put this back into the left side of the equation, I'll have a e to the t, I'll actually write this out, minus 3a e to the t plus 2a e to the t equals e to the t. And if I factor out the e to the t's, I'll have a minus 3a plus 2a equaling, well, e to the t. And so really what I need here is I need 0 to equal 1. It's like, oh man, this doesn't look good. This is bad. Okay, so what am I going to do? Just like when I had this kind of issue with the repeated root, had overlap when my characteristic polynomial, when this was homogeneous, and the characteristic polynomial that this induced gave me back a double root. It's like, oh no, what do? I just attached a t to it and it ended up working. And that's basically what I'm going to tell you is that we're going to do the same exact thing here. Okay, and it's going to be a little annoying, but we can do this, right? So off to the side, I'm going to kind of copy down my solution to the corresponding homogeneous, right? If I had y double prime minus 3y prime plus 2y equals 0, then I would have had y, the general solution for that, or maybe I'll just say y1 is c1 e to the t, and y2 is c2 e to the 2t. Okay, just from, finding the characteristic polynomial, factoring it, using the solution that we already have for that situation, that's what you would get. now I'm going to try to see what happens with y equals t e to the t. Now, that would be like, you know, at the very beginning, I was like, oh, I'll just try e to the 3t when I had e to the 3t over there. And it's not going to quite work, right? I need to use the method of undetermined coefficients, and so in order to do that, there's going to need to be a coefficient. So it's going to be a t e to the t. Okay? Now that means that y prime will be a e to the t plus a t e to the t. Because the product rule. First, I took the derivative of at with respect to t, left e to the t the same, then I left this the same, took the derivative of e to the t, and I can see where this is going to happen. For double prime, derivative of a e to the t is a e to the t, and then the derivative of this is the same as, well, what I did above, so I'll have this. Okay. And maybe I could combine these together and say that's 2a e to the t plus a t e to the t. All right. Okay, now I'm going to go and I'm going to throw this into the left side of the equation, right, and set it equal and try to figure out what a's give me this. Okay. Then, all right. Okay. Y double prime. 2a e to the t plus at e to the t plus, nope, negative 3. So minus 3 y primes will be minus 3a e to the t minus 3at e to the t plus 2y's plus 2a e to, I think there was a t in there, right? Yeah, 2at e to the t, 2y's, and that's equal to 1 e to the t. Okay, right now I'm going to go through and I'm going to rid myself of all of the e to the t's. I'm going to divide this whole equation by e to the t, so I'll have that gone, here we go, and then there I'm left with a 1. So maybe I'll write that in. Okay. And now I'll have 2a plus at minus 3a minus 3at plus 2at equals 1. And how's this going to work? I know I've got really everything that has a t together. I need to put together. 1 plus 2 is 3, minus 3 is 0, right? So that's 0. I have 2a minus 3a is negative a equals 1. So I'm thinking that a is negative 1. Right? And so, kind of my particular solution is going to be y equals negative t e to the t, which is what I had called y hat earlier. So y hat is going to be negative t e to the t. And so my general solution is going to be y of t equals, all right, well, it's the homogeneous solution, c1e to the t, plus c2e to the 2t, plus, well, this negative t e to the t. It's a particular solution. Okay. And if I have some sort of initial conditions, like, I don't know, maybe probably want to work with t equals 0. So, you know, if, for instance, they gave us initial conditions like y of 0 equals 2 and y prime of 0 equals a negative 3. I don't know. I haven't worked this example all the way with initial conditions, so I don't know if I've just boxed myself into a bad scenario, but it'll be all right. So if y of 0 equals 2, then I'll have 2 is equal to c1 plus c2 plus minus 0. Okay. And if y prime of 0 equals negative 3, well, I'm going to need to take y prime y prime is going to be c1 e to the t, 2c2 e to the t. Minus e to the t minus t e to the t from the product rule. Okay. Yeah, okay. And then, yeah, y prime of 0, that's going to be all right. If I have that being -3, will be equal to c1 plus 2c2. Okay, I know from linear algebra this is going to have a solution. Minus 1. Right, if we have different slopes here, we will have at least a solution. It might not be very good, and I just have to solve this system for C1 and C2, right? So maybe I'll go and I will do that. I'll grab a different color so you can see what I'm doing here. I'm going to go over here, and I'm going to take this, and I'm going to solve it down below. So I have 2 equals c1 plus c2. I add 1 over there, and I'll have -2 equals c1 plus 2c2. Okay, if I subtract equation 1 minus equation 2, I'll have 4 equaling c1 minus c1 is 0. C2 minus 2c2 is going to be -c2. So I know that c2 equals -4. And then over here, if let's say I want to eliminate on c2, so I'm going to need to take equation 2 and subtract 2 of equation 1. So I'll have -2 minus 4 is -6. Okay. So if I take this one and I subtract 2 of these, I'll have -c1, which means to me that c1 is 6. And in conclusion, my particular solution to that differential equation with these initial conditions is going to be y of t equaling, what is it, c1, so 6 e to the t minus 4 e to the 2t minus t e to the t. Okay? And that's my particular solution. And this is the method of undetermined coefficients. Now, before I end this video, I'm going to answer the question that you probably have, like, hey, what if this is not just some like power of e, right? What if this is really anything else besides an exponential? And I've got basically a list of guesses for you. Right, because we guessed exponential is going to be exponential. I'll show you, and then any kind of combination of those, you would use a combination of guesses, and it can get pretty nasty algebraically, but there's plenty of practice out there for you to, hone your skills on that front. So what I'm going to do, I'm going to pause, I'm going to write down the list of guesses, and then I will, and then I'll just explain what I'm doing here. All right, so we're dealing with this linear differential equation that is not homogeneous. And the non-homogeneous part is polynomial, right? Like, basically, a0 plus a1x plus a2x to the 2 up to an x to the n, right? It's some nth degree polynomial. What we're going to do is we're going to guess an nth degree polynomial. Hold on, let me just look and make sure I'm writing this down right. All right, yeah, the book was using A0, A1 for the guess, but I'll just use something else. Guess that y hat is going to be, maybe I'll just use A0 plus A1x up to ANX to the n, right? You're going to try to figure out all of these are undetermined coefficients. If g of t is exponential, like something, I don't know, e to the rt, we're going to guess, some number times e to the rt. Like I already did that. I already showed you how to do that. A e to the rt. That equals a e to the RT, and figure out what a is. Determine that coefficient. And if g of t is trigonometric, you know, like sine of kt, or maybe cosine of kt, then I'm going to suggest that you guess y hat be a combination of sine and cosine. So that's the thing about that is, just show you what I'm saying. Y hat is a cosine of kt plus b times the sine of kt. Because it is entirely possible that, you know, one of these will come back 0. But it might not be the one you expect, or you might need both of them, depending on the differential equation and depending on the initial conditions, I think, or, you know, depending on the initial conditions. I don't think it depends on that. But that's what we're going to guess based on what is our non-homogeneous part over here. So to conclude, I'll answer the question, what would I do if I had some sort of like combination of these, right? If I had, I don't know, maybe the sum of them and maybe 2 are multiplied together. See, I'll just erase and give you a differential equation. I'll show you what guess to use. I will not take it all the way because this is already a very long video, right? And the one I write down, I'm going to just make it up off the top of my head, and I don't think it's going to be one that if you did, it would work out very nicely. All right, there we go. So, you know, suppose I've got, you know, constant coefficients, and this is the non-homogeneous part is e to the 2t times sine of t3 times t to the 4, right? Just like as bad as I could think of. I probably think of worse, but I'm going to use y hat equal to, okay, for the exponential is connected to the trig with multiplication. My guess needs to have exponential connected to the trig through multiplication. So it's going to be a e to the 2t sine of 3t. But I also need to consider, you know, I might could have some cosine in there too. Plus b e to the 2t cosine 3t. And then t to the 4, what I'm going to need is I need a fourth degree polynomial. So I'm going to need c plus dt et squared ft to the 3 gt to the 4th. It's going to be a lot of undetermined coefficients, right? So yeah, I'll just write that in here. C plus dt plus et squared f times t to the 3rd, and finally g times t to the 4th, right? Okay, this would be my guess. I would run this through the second derivative. I'd end up with a bunch of things that I could, you know, use some algebra to find the values of a, b, c, d, e, f, and g, and then I could maybe after that use my initial condition to find a solution to this thing, but I'm just going to leave that there. That'll be all for today. In the next video, I'm probably going to tell you about how to use power series to solve some troublesome differential equations.